Hey, and welcome back, everyone. I hope a few people are joining already in a bit. Yeah, and sorry for not streaming last week. I was unfortunately at a conference. Well, that was the fortunate part, but the hotel did not allow for streaming. So, yeah, the Wi-Fi was broken, as it sometimes happens in hotels. So, sorry again. Yet here we are. For those who are new to this, we are looking at a VisionFive RISC-V single board computer here. And what we're doing is we're writing firmware for it, or at least we're planning to do so. And what I've prepared today is, well, first of all, an additional camera. So what you're currently seeing here is a very close-up view of the actual board. On which you currently see the SoC, that's like the CPU and peripheral controllers. You see right in the middle a piece of DRAM, so that is, where the computer has its memory. And then around that a few labels, the VisionFive label on top and the StarFive logo on the left. That's the company who made the board. And let's now see again what we did last week. To get a bit of a recap first. And for that, I have already opened the website again. So this is StarFive's website on starfivetech.com. And as you can see, they have this board here presented very nicely on their website. And I received one of those for the developer program from the RISC-V Foundation. So last time, we had a very close look at the hardware already, so we went through all the peripherals, all the connectors that you can see on the board. And what we're going to do today is we will take a deeper look at what is actually inside of it. So we will look at something that is called the mask ROM, and we will see what the boot flow is with the current firmware that is already on the board, which has been shipped with it. And to not tease you too much, let's look at the documentation actually, which we already did also last week, and see how the firmware has been built originally. So they have a bit of a manual of steps for providing your own firmware and then also flashing it onto the board. And today we're going to see, what the result was when the vendor did it themselves. So this here is from the so-called software technical reference. It's not very technical though. This here is more end user oriented, but it's okay to repeat the steps for building the software. And this section I already opened here is on compiling the bootloader. And the bootloader is what is taking over after the mask ROM, which is the part that is already fixed in the hardware and cannot be changed. That is taking then over. So the bootloader is, in that sense, the second stage of the boot process. So we looked at the flow chart also last week, and it started with the second stage. And if you may have wondered why that was the second stage, that's why, right? So the mask ROM comes before it. So yeah, it's also written here. It's called JH7100 second boot. And it's actually in a repository on the website. So the general procedure would be to just clone the repository, just like you do with any other software that you want to compile, right? You need to obtain the sources and then type some commands to build it. In this one here, it's just the make command. The make tool is a very general Unix tool that many people know. It's really just for executing tasks and initializing that. So yeah, this is already provided, so you don't really need to do much. And as you can see, this is only one of the many pieces. The next one would be the DDR init. So DDR is just a type of DRAM or memory actually for the computer to work with. There are different kinds of memory. Even within one single computer, you usually have many different sorts of memory, starting with the so-called registers, where you can just store, a number. Not too much. Usually it's like 4 bytes or 32-bit, if you will, or it can also be 64-bit. That is what modern machines are doing, and sometimes even 128 bits. But if you want to go up to megabytes and gigabytes, you will need to have some other sorts of memory. And that is where RAM is starting. There is so-called SRAM, the fixed RAM, which is where mostly those bootloaders are being executed. And then on top of that, you have DRAM, which can go to gigabytes and sometimes even terabytes today. And so this is what is being initialized here in the second part. I have myself never really dealt with that very much, but I did so very recently for another RISC-V based processor, which is the Allwinner D1. And for that, I have translated the existing code that was provided by the vendor, which somebody had already translated to the C language. I took that and translated that yet again to Rust, and we just got it to work over the weekend. And so we're at this point where we can already fully boot that, and all the code then is written in Rust actually. And that's also what we want to achieve here. And in the process, we're going to learn how the platform actually works, really like from the ground up. And let's see where that takes us. So yeah, those steps here, I just wanted to take a brief look at this because you will see a reflection of that when we're going to take a look at the boot process in a bit. And now we need to look at another third part even, which if you remember it from last week, is U-boot. And that would typically then eventually load the operating system. In this case here, it would be the Linux kernel, which is also described here. So yeah, the third step would actually be compiling U-boot. And technically, if you want to boot an arbitrary operating system, you would already be done at this point, right? So if you don't want to boot Linux, but you want to say boot FreeBSD or Oberon or Plan 9 or one of these many other operating systems, then you would need to do something else at that point. Or you would need to provide a bootloader environment, which gives you, again, flexibility. So that is also a very typical thing that you will find. Nevertheless, so yeah, just for recap, we now have these three components here. We are starting with a so-called second boot, so what is coming after the mask ROM. Then we're initializing the DRAM, that is the second software part here. And then we will start U-boot. What I have already prepared today is I hooked up to both of the serial ports on the board. So last week we only connected to one of them. That was the one which is directly talking to the mask ROM. And the mask ROM itself can be, well, you can boot right into it, and so not handing over to the second bootloader. You can also stay in it and interact with it a bit. We did that to see what actually happens and how it works. It is very, very basic, as you may understand, right? So it's really just the fixed part of the hardware, not changeable, so it has to be very reliable and minimal. That is also what we want from firmware in general, but let's put that detail aside for now. So I will now switch to the camera again and show you around because it's yeah, maybe to some people who have never done this before, not too intuitive. So what we are currently looking at here, and I will now look at this in detail in a different view. So this is the board, as I said, and we're just looking at a very small portion of it. I would say maybe a tenth or maybe even less. So I will put my finger somewhere here now. As you can see, this part here is very, very small. So let's move around the board a bit and head over to where we also hooked up last time. Just hang on a second. And here we are. So this header that you see here on top, right? So these three pins, they are one of the two so-called UARTs, or serial ports, if you will. There is a ground pin, the leftmost one. That is the most important one to connect in the first place. That means that both this board here and also what I connect to it have the same reference level for voltage. And then relative to that is any other level that we apply. So there are two more pins here. They're called TX and RX for transmit and receive. And they are relative to this ground pin. That's why we always need to have this ground pin connected. Otherwise, we wouldn't be able to retrieve or send anything properly. So this here being connected means we can now monitor what is going on there if the mask ROM boots up. And right above this here, there is a special button. So you see there is one button this here, the reset button. I can push this here from the edge. And then there is a second one, which is a bit hidden. So hang on a second. So that one says, it's really hard to see it. Okay, now you should be able to see it. It says boot mode. And what this does is when you keep it pressed while powering on the board, you will enter the mask ROM. And now let's do the following. I will switch back to the other scene again. And let's have a look at the terminal. So I already connected this here. And also the other serial port that you find further on the left. That one. So if you know the colorful header here on top, it's just like on the Raspberry Pi, very similar pin order. And the third one from the top left is always ground. And then we have the other two pins again for receive and transmit, just like on the other header. So what I've connected to this is now two serial converters that run into my laptop, right? So now on my laptop side, in my terminal, I can look at both of these serial ports and see what's happening. And so let's see. On the left-hand side here, if I remember correctly, I have what is then displaying the mask ROM. And on the right-hand side, I have the second serial port, which is going to display what we just looked at in the manual. So in the first step, I will now power on the board and I will keep the boot mode button pressed. We also did this last time, and let's see what happens. That looks very much like nothing is actually happening. And the question why is very hard to answer sometimes, but I do have a suspicion. So it can easily happen that you mess up the order of the pins. So there is one pin for sending and for retrieving, right? So if you mess those up, there is something going wrong. But I actually noticed something that we already figured out last time. Look at this number down here. We figured out, and that's written in the manual, that we actually have a different transfer rate on this one. So we need to switch this. This here is like a very typical one that you see on very, very many cases. We need to switch this to 9600. We're going to do so now here in the serial port setup. I will change the BPS to 9600, just using some shortcuts here. If you are having trouble following that, just recap the video from last time. You can see the recording online. By the way, I'm already doing this. I always upload everything again to YouTube so that it's archived there, because here on Twitch we only have it for like 14 days or something. Okay, so now the baud rate is switched. And you might notice that the cursor has actually moved. I don't know why, but it can happen sometimes, you know, when you touch something. Technically, all of that, you know, can give you some current. Anyway, let's power off the board again and keep the boot mode button pressed while powering on. And here we go. Now we see the SiFive greeting again. The copyright, always important to many, many companies. And then the hash, and now we could enter something. So last time we figured out from the manual that there are a few commands that we could type now. Now I want to do something different this time and actually look on the other side. So if we do not interrupt this boot process, what is going to happen on this side here? And for that, I'm now going to press the reset button, but I'm not going to push the boot mode button at the same time, which means that we enter the regular boot flow. And as you can see here, now something else is actually happening. I just hit the return key so that we would interrupt this process here for now, so that we can stay here and see what is happening. So first of all, it starts with something saying bootloader version. That might be the first bootloader that we saw in the manual, which is commonly referred to as the second stage. And then we see something about DDR already. So this is definitely the next stage that we just looked at in the manual, which is initializing the DRAM. So on this board here, we have 8 GB of DRAM. The one chip that you saw in the camera is only one of the two. There is a second one. So each of them is 4 GB in size. And so what this here is doing is it's initializing the controller that is talking to this DRAM, and then potentially training or using some hard-coded values to figure out the delay between the SoC and eventually the DRAM module. So DRAM is very, very timing sensitive, right? So you want to access memory very, very quickly, which means you are at very, very high speeds. So you need to be very careful not to go too fast at some point or be a bit too slow, right? So timing is really, really critical here, and this is why you need to go through this step. That is also happening on your laptops, by the way. So what the firmware on your laptop would do is just the very same thing on startup. All right, so we get some additional feedback here. One is the clock rate. So this here is saying 2.1 gigahertz or 2133 megahertz. So this is already quite some speed. What I'm working with the other boards here is a bit on a lower clock rate, something like 800. So yeah, this is almost 3 times as fast. So it's something that you can already work with very, very well. I think this is also the speed that you would have in a typical laptop nowadays. Anyway, it says flash programming. I'm not sure why it says programming. It sounds a bit odd, but what it's doing is it's presenting you again with another menu, and it looks like there is already something here built in for updating. So the first option that you see here is to update UBoot, from which we haven't yet seen much. So we will continue with the boot process here again in a bit. And the second option is to just quit. I assume that when we say quit, it would just continue with the boot flow. So let's actually try that. We enter 1 and hit return. And it looks like nothing is happening. So yeah, then I guess the board was just, powered off. Not fully, but there are different states for a CPU. Anyway, so I'm now going to hit the reset button once again. And then we can look at the full flow. And here we go. Card did not respond to voltage select. Okay. So yeah, now we are somewhere else. It says VisionFive down here. We also have a hash, so it looks like we can interact with this again. But before we do so, let's scroll up again and see what else we could have seen, because it was quite fast. Oh, look at this, some ASCII art up here. Okay, so this here is what we had already seen, right? So it says bootloader and version, the DDR clock rate. And now this here is from the countdown. So it counted from 2, 1 to 0. And now it's doing some checks here. So it says CRC. That is for cyclic redundancy code. It's one of the typical codes that are being used for, verifying the content of, it can be a file, or in this case here, it's what has been read from the flash part on the main board. Yeah, there are 2 CRC checksums. So one of them is for the flash and one is for DDR. I would assume that those are actually the separate stages. So when it says flash here, maybe it is from the previous stage, although that sounds a bit strange because we already passed it. And DDR, well, we also passed that already. Yeah, whatever. Maybe it's just an assertion that indeed what happened before is okay, and we can continue booting. So what it says now is bootloader. And well, if we are a bit picky, we actually had a few bootloaders already, right? So yeah, you can imagine any stage always to be a sort of bootloader. So you start in an existing state, you do something, and eventually you execute another stage. So that process of executing something else again means we're loading something and then executing, and that is essentially what it boils down to when we use the term bootloader. Anyway, we now see something that we hadn't mentioned yet, and it says Open SBI. So I don't want to dive too deep into this, but I can already tell you that SBI, so the part after Open, is part of the RISC-V specifications. So it's short for the so-called supervisor binary interface. And that interface can be used by operating systems to call into the firmware and perform certain operations, maybe ask for some information and so on. And the idea is to have some separation between higher privilege code that could be executed and the lower privilege code, which is commonly an operating system or, can be a hypervisor and then another operating system behind that or something. So yeah, they made this very nice ASCII art here to make it look very appealing and friendly. That's actually very nice. And now we get some more information again. So what we see here is very similar to what we could also find in the data sheets. There are some very specific details here, which I also don't want to go too deep into right now. But there are some things that we can get an understanding from, which will carry us along for now. So the first thing here, well, the vendor and the board name, of course, StarFive VisionFive, that's the board we're looking at. Then it's saying MEDeleg, and that is for delegating. M is for machine mode, and E is exceptions. So there is a feature on this platform which allows to delegate exceptions which are happening in the machine mode. So in RISC-V you have different modes. One of them is the machine mode, that's like the initial mode. This is where the firmware here starts. And then there is the supervisor mode, and hence also the name SBI for the supervisor binary interface. And that supervisor mode can also take care of something like exceptions. There are also interrupts, it's not yet mentioned here. But anyway, so from machine mode, you can also delegate those to the supervisor mode. And that is probably also happening here. Yeah, so down here, you actually see a few more details at the very bottom. So MEDeleg, this here just means very, very specific so-called exceptions are being delegated. So if we look behind the details of this mask and into the specification, we can figure out what exactly those are. Let's just take it for granted now it's some exceptions, okay? And the same I already mentioned, interrupts, MEDeleg, that is delegating the interrupts. Here we also have some interrupts which are being delegated to the next stage, which would be commonly the operating system. Okay, but let's go back to the top again and just continue. The hard count, here it says 2. And hard is short for something which is roughly like processor cores. They just wanted to have a different name for RISC-V. I haven't looked that much into detail here myself, but yeah, let's just assume this is like processor core. So, at some point we had single core machines, and then people thought, well, it's getting hard to get those up to speed. So how about we have multiple cores in one of those machines, and then we can split compute intense operations, right? So there are some which can be very efficiently distributed to multiple cores, or on the RISC-V platform, it would be hearts. Then there are IPI and timer devices. There is something called AC-Lint or A-Clint. Could also be that they want you to pronounce that way. For this, we will have a very, very, very brief look here at some of the specifications in RISC-V. So this here is the PLIC specification, the platform level interrupt controller. And interrupts, which we already saw, can be delegated in part, right? They're a very essential feature of a platform. And among those interrupts are, for example, timer interrupts. You can set a timer, just, like you would set your alarm for getting up the next day. You can say, hey, please wake me up again in whatever, milliseconds or something. And then one of these interrupts will be triggered, and then, you would get a signal somewhere, which is then called the interrupt. And then oh, something is happening. And from there, typically you would implement some routine which is handling that. So timers are a very, very common thing to use. They're very essential to computing anyway, right? So anything that is timing sensitive is based on that. If you're using let's say high-level programming languages today, like for example JavaScript, you can even use them there. So if you are in a web browser, we can have a very brief look at that. You can go to your console and you can say set timeout. And with the set timeout function, you can say, hey, execute this and this function in these and these, I think it's milliseconds here. So we can say something like, we write to the console here, and what we're going to write is RISC-V. Sorry, I'm being a bit too stupid to type. And this should now be triggered in, let's say, 1 million milliseconds, right? No, let's say 1000 milliseconds. So that would be in a second. Or let's make it actually 5000, so we can count to 5, right? So when I hit enter now, this function will be executed, and after 5 seconds, we should see RISC-V. Okay, so 1, 2, 3, 4, 5, and there we go. You see, it says RISC-V. So yeah, the timer interrupts are the primitive to that. And the specification here is essentially summarizing this. If you want to implement your own RISC-V hardware, you would need to conform with this, so that somebody now programming on the platform can do so accordingly. All right, and with that, let us get back to the serial here. Okay, so yeah, we briefly talked about timers. So the timer device is what is behind that. There is a console device. You also see this term here that I've used a bunch of times already, UART, the Universal Asynchronous Retriever and Transmitter. This is a specific type. If you search for 8250, or you may now find 16550 these days, this is a very, very common one from very, very early days of computing, and it's evolved over time. But because it's such an essential thing, it has sort of become a standard sort of thing to implement. Yeah, we're not going to look into details of this now. So in reality, I can also tell you that there are hundreds of variants of this, but they're similar enough so that it's mostly easy to port code from one platform to another, where you might have a slightly different UART, but the general recipe of talking to that is very, very similar. Okay, some devices are not present, and let's just ignore those for now. Another interesting thing is the firmware base. So if you look at this here, this is 8 3 zeros and another 4 zeros. This is a memory address. So the firmware was loaded to this memory address. And if I'm not mistaken, this here should now already be the DRAM address. So if you remember, we did the DRAM initialization. And now we can keep executing from DRAM, and that happens at this point. So the firmware being loaded to this address is this here inside 300 kilobytes. So to be honest, for firmware, this is already quite much. So 300 kilobytes, this is already the size of a very stripped down Linux kernel, very much. So yeah, I don't know what is exactly in there, but we will figure this out at some point. Okay, now they're talking about domains here. There is this domain 0, and there is something about the so-called boot heart. Yeah, let's also not go too much into details here. I just want to tell you very briefly, what they're not mentioning here is a term in RISC-V which is called PMP, physical memory protection. So yeah, they are calling those here regions. With PMP, you can apply several protections to parts of your memory. And if we look at this here, we can see this is an interesting part now. Region 01, which starts at 8, 3, 7 zeros. So this is exactly this address here. And then ending at this address. This part is protected. So this here means that you can't just simply read from it or write to it or execute something in that memory space. But you can do so in the overall space. Now I'm a bit unsure, to be honest, whether this here wins over that one. It should, otherwise it wouldn't make sense to make everything accessible. Yeah, we can also see this part here. I would assume that this here is the SRAM, so that is the the hard part of the memory that is also part of the SoC. It says I. I'm not sure what I is short for, but RWX definitely means read, write, and execute. So if you come from Unix and you know this from file systems, the same thing is being applied here in memory, right? So yeah, the design is sort of the same in that sense. Okay, now there is something else. It says next address, and this here is also very interesting. If you write your operating system now and you want to be executed after this firmware part, this means that you would, if you now write your own software, you would need to link at this address. So you need to know where in memory you start, right? And this is the address. So this is also very common and typical. If you look at the Linux kernel, it would also compile in such a manner that it's linked at this address here. Okay, and then there is next arg1. So it's also very common to not just boot something else like the Linux kernel, for example, but also to pass along some information. And what this here is saying is, just a later address, arg1. This is very likely the so-called device tree. That is what is telling Linux what to expect on this board here. So there are different ways for an operating system to figure out what is actually on the board that the system is running on. One of them is active scanning, right? So depending on what you're dealing with, let's say PCI, for example, that allows you for discovering things yourself. But there are also buses where it's not as straightforward and the firmware actually needs to tell you something. So imagine that just being, like a rough plan of the board. Let's say somebody, took a piece of paper and just noted down, okay, here you will find, I don't know, the video output, and there you will find the serial port and so on. And then it's handing over you that sheet of paper. So this is sort of what is happening here. Now it's also saying the next mode. So the next mode would be S mode or supervisor mode. And then it says something about sys reset. I'm not sure what they mean by that. It might be that there is a capability to say I want to reset the system, but yeah, we will figure this out maybe at some point. Okay, now there is the hard ID. So yeah, the 0 hard. That is also sometimes referred to as the boot hard. So we also see this up here. This is where we start the boot process. And then we see the ISA. So this string here is a bit longer than what we looked at last time. So last time we also looked at the Wikipedia article, which is describing the RISC-V architecture. And it's describing each of these letters here. And I actually forgot something last time. So we looked at this here, IMA-FD. There is also a short term for this here, so you don't always need to spell out everything. I'm not exactly sure, but one of those is also part of it. There is a G letter, which is short for a bunch of these here. We can have a look at that again on Wikipedia. But for that, I want to copy the string so we can, we can now keep this here in memory. So, do we still have this somewhere? Yeah, I have a lot of history. Anyway, so we just search for wiki RISC-V. That very easily takes you to that place here. And here we go. So we have this table down here, which is explaining all the different letters. So what did we have actually? I just quickly opened another terminal just so that I have something to paste into. So it was saying RV64. This means we're on a 64-bit architecture here. And we have the base integer instruction set, right? Now we have M, A, F, D, these here, multiplication and division. We have atomic instructions, single and double precision floats. So we can not only use integers, but actually floats, which are like fractions, for example. And then there is something C. And what is C for? C is for compressed instructions. Okay. That means you can have a more compact representation for multiple instructions maybe, right? So that makes sense. Then it says S. S is for standard extension for supervisor level instructions. Okay, that also seems to make sense. Then there is a U. Where do we find the U? I don't see U up here. Maybe it is one of the features which are in development. Huh. Interesting. Anyway, it also says X, which I don't see here either. Okay, so let's ignore those two for now. But I want to get back to this here, the IMA-FD C. Well, the C is not part of it, just IMA-FD, because we looked at that last time. That is also grouped together as G. But there's something else which is behind that, and that is ZICCR. And that is actually ZICSR, right? So I forgot last time and I haven't really found it. It's actually right here in the table also, so I was looking at that in that very moment as well. This is for accessing so-called control and status registers. If you have ever done very low-level development on the x86 platform, they have something similar. It's called MSR. If I remember correctly, that is machine-specific registers. So the idea is that you have something where you can ask the machine, hey, what is this here, right? And some of those registers can, for example, reveal to you, let's say, specific features that are on that platform, or the vendor of the platform and things like that. Okay, there's another thing here, ZI fence I, fence I, instruction fetch fence. Okay. Yeah, we're also not going into detail now, but yeah, I just wanted to mention that it's actually written here in the table and I forgot this last time. Yeah, we will have to deal this maybe at some other point. But for now, this here is okay. All right, so let's get back here and let's see what else we saw in the boot process. So yeah, I just skipped another few things here because they're not too important right now. PMP already explained that above. right? And I'm actually not sure what MHPM is now short for. Anyway, so let's look at what we see now for the third part, which is now U-boot. So it says the version, the vendor, you know, the build timestamp and so on, which is very nice. And here again, it's giving us information on what this platform actually supports. So we just had another look at that. We see the model again, right? So the name of the vendor and the main board. Now we also see the amount of DRAM. We haven't seen that before, but that's okay. Now we know. And now we see something about cores. So there are 13 devices, whatever those are. 9 U classes. I'm not sure what U classes is supposed to mean in that sense here, but it says something. Device tree, which I also mentioned before. So it says the device tree is separate. So I just described that the Linux kernel can be given something that describes the platform to it. And the same is also true for U-boot. And in fact, they can even share almost the same device tree. Sometimes it's really the very same thing. Sometimes you need some minor differences. Okay. MMC. So MMC is a part of memory. Here in this case, like if you think of an SD card, for example, that can be it. There is also eMMC. I think the E is for embedded or something. That is something you might find in, I don't know, phones sometimes. There can also be other variants. Anyway, and now it's saying loading environment from SpiFlash. So the SpiFlash is something that is also on the board, and this is actually where the previous stages were already loaded from. So this is happening over and over. So each of those stages is loading something from the SpiFlash again, starting already with the very first, the mask ROM, right? So the mask ROM is already probing the SpiFlash to see, hey, is there something I can boot, and then starts executing it. Depending on the platform, you know, something might be necessary to set up very specifically for that. But let's just assume that this is where the execution starts. Now, SPI, the serial peripheral interface, we also looked at that very briefly last time, is provided through something made by Cadence. So Cadence is one of the vendors that make these so-called IPs, or intellectual properties, which is a very strange term in hardware, and it's actually, you know, just part of the SoC. It's, in this case, it's the part that is controlling the SPI, the interface. That's all it really means. Everything else is for lawyers or something. It says can't get 4SF, whatever, but it detected something, and what it detected here is the name of the flash part. And I already looked at the board to verify this is really the right thing. It says GD. GD is Giga Device, one of the vendors, 25. That roughly describes the form factor. I'm not exactly sure about all of them, but I think this is part of the format. And then LQ128. We can just have a brief look again what this may be. So here is a data sheet that we find very quickly through Google. It can be sometimes on some website. Commonly, it's also the vendor's website. Sometimes they don't provide data sheets, so then it's very, very nasty, and you need to hunt a bit. Yeah, but often you would just find them right away, and then you can actually work with them. So yeah, this is what we saw, right? So GD25 LQ128. Now there's a D behind that. Let's see what we had here. Oh, we didn't have this D. But yeah, let's assume this is okay for now. Now these parts, they can also have many different variants. So yeah, there can be whatever letters behind here. Let's just ignore that for now. There is one important thing to know. This here is running at 1.8 volts. So if you want to interact with the flash part, not through the board itself, but directly, let's say you want to attach a programmer, then you would need to have something on this voltage level. I tried doing that last time without success though. it could be that it was actually the wrong voltage. So yeah, you should actually be careful with this. So if you supply too much voltage, it can damage the part. But yeah, it hasn't happened to me yet so far. I know people that had this happen. So yeah, just be very, very careful, especially if it's not your own hardware and you're doing something for someone else. Anyway, yeah, what is typically described here is, the commands that you can send to these flash parts. So for reading out data, for writing data, and so on. Okay, now let's get back to here. We get a few more details. For example, what do we have here? Here, the Ethernet MAC address. So this is the hardware address for the Ethernet interface to which you can, connect your router or something. And then the router can say, hey, I'm assigning an IP address to this here, if you want to have it in your network. Okay, and now it's saying MMC, card did not respond to voltage select. That is a very odd message to say, but that's okay. All this means here at this moment is there is no SD card in this board. And that is because I never inserted an SD card. So we end up here in the bootloader. And I want to have a brief look again at the datasheet to see the size of the SPI flash here. So this 128, this is typically the size in megabits. Now if we search for 128 right across the sheet, yeah, we should also see this here, there, 128 Mbit SPI flash. This means, in other words, 16 megabytes, or they also have it in kilobytes. 16 megabytes is more than enough for, let's say, a Linux kernel with a small environment around it, or also other operating systems. It's a lot of memory. So technically, it feels a bit like overkill on this board here, but it also means that we could embed a full boot environment on this here, which is a bit richer than what we're currently seeing here, and make it a full Linux system without any SD card at all. And that is also something that we're going to do over time. Okay, but we're now in a shell here, which looks like it's from U-boot. And I know this shell because I've been working with that for a bunch of years now. And the first thing we're going to try is we will say help. And this should give us all the commands that we could enter, which are quite a lot. So this might explain why the firmware is 300 kilobytes in size, as we saw earlier, right? So yeah, let's look at a few of those commands here. One of them is bdinfo, so we can get some board information. I haven't yet seen much of that really in place. Yeah, then there are a few boot commands, for example, boot elf. So elf is a binary format that is also commonly used for the Linux kernel, for example. So if we have the Linux kernel in an elf format somewhere in memory, we could use this command to boot it. Yeah, there is also other formats, this image format here, for example, which is essentially a raw binary, which is also something I frequently use because it doesn't have any overhead and doesn't require additional parsing or otherwise handling. Yeah, and then there are a bunch more. Let's ignore them for now. There is also something called CBFS. So CBFS is short for Core Boot File System. And Core Boot is a project which we had forked at some point. And that is originally written in C. And we have removed the C and we don't call it Core Boot anymore. We call it oreboot. And oreboot is written in Rust. And that is what we are going to work on eventually. But it's nice to see already a reference here. I hadn't expected that. So this was a very positive surprise now. Anyway, there is also something called env, which if you want to hack on some of your gadgets sometimes, it can be very helpful to look at that because it shows you some variables set up for booting the system, and so something like that. Yeah, then there are a few more commands to deal with different file systems, like the FAT file system, for example, which you may know from DOS, or Windows is sometimes still using it for USB drives. Then there is the ext file system, or extended file system, I think. This is commonly used on systems like Linux, for example. We now have ext4, so this is like a more modern variant. And then there are many, many other commands. So this was just a very brief look at that. So what we could now do is, from here, we could boot an operating system. For example, we could boot from an SD card. I could now take an SD card, put a Linux kernel on it, and then use those commands to boot from that. Or do so over the network. So there's, for example, the tftp boot command, the tftp protocol. I'm not sure actually what the last P is for. Anyway, it's for transferring files. Oh, right, FTP. That is the file transfer protocol. So the protocol after that is redundant. And the first T, I think, is for something that should mean something like simple, but I forgot the word it was. Trivial, right. So this would be the trivial FTP. Anyway, yeah, so as I'm saying, we could now boot an operating system, but actually wanted to dive deeper into the platform. And so what I want to do now is, sorry, so we can look at memory here also. And what we can look at is, for example, the mask ROM itself. So if you remember from last time, we had the mask ROM's address documented. So what we could do is, we could read out the mask ROM and then write it to a storage part. But of course, this only works if we can actually read that region from memory. So what we would do is, we would read from the SRAM and make a copy of that to the DRAM. And let's see if we can actually do that. So yeah, it might be that the physical memory protection that we saw earlier is preventing us from doing that. And if so, then we will need to write our even lower level firmware, which is replacing those early bits, so that we can access the mask ROM. So now let's have a look again at this here. Either this or there was another manual. Here it says updating. There was something for recovery. So let's see if we can find that here again. Otherwise, I think we actually need to look at the other sheet. Right. So yeah, I downloaded a bunch of documents actually. So there are the JH7100 docs, that is for the SoC. Then we have something for the VisionFive itself. So this is a larger repository. I think this is actually, yeah. So these are, I think the schematics. Yeah, right, SCH, that is for schematics. Then there is a bottom and top view of the board, but that doesn't interest us right now. What we want to look at again is the quick start guide. So right here, we had the bootloader recovery. And so this here was the SRAM address. But this is, now I remember, this is actually not where we find the mask ROM. So this is the memory that you can use, and the mask ROM was right behind that somewhere. And that is what we find here in the SoC datasheet. So this is where we have the same address that we just saw. But here it's documented which parts are which. So one of them is saying ROM, and this should be the mask ROM. So we start at 0x1840 quad 0. And then we have a bunch of bytes behind that. So if I recall correctly, 1000 here in hex would be like 4K actually. So 4,000 in decimal. Anyway, let's see if we can read from this. So the U-boot shell should allow us to say, let's see, something like copy or load or something, right? So CP for memory copy. Let's say what we get when we say help CP. Okay, so we say CP, then a source, a target, and a count. So the source would now be, let's have a look again because I don't remember that, 1840 quad 0. Now we define a target, and for the target we're going to use the high RAM. So I'm going to use, I don't know, 85 and then lots of zeros. Now we need a count, and I'm not sure what the size here was, so let's have a look again. Right, it's hex 8000 again. So let's see if this works. There is no feedback here. So let's try something. There is another command that we can use, which is the CMP command, and the CMP command can compare memory. So let's see what it says. We say compare address 1, address 2, and then the count. So instead of CP, we are going to write the very same thing, but with CMP. And then again, we have two addresses and the size. And it says 32,768 words were the same. And what is a word? A word is 32 bits, I think. So that would be 4 bytes. So if we multiply this here by 4, let's do so in my favorite calculator, which is Node.js. We calculate that by 4. This is 128K. Or if we want to have this in hexadecimal, too stupid to type again. So we're now saying to string 16, so 16 is for hexadecimal, and this is 20,000. I think that's a bit much, is it? So 2 and then 4 zeros, and here, oh, it's actually not enough. Oh, yeah, we're missing something, or aren't we? Hang on, this should be like 8,000. Let's maybe not multiply this. Okay, now we get 8,000. Okay, this is the moment where I'm confusing myself once again with all the different sizes of bits and bytes and words and halves and doubles and whatsoever. Let's put this aside for now. If you're dealing with that on a regular basis, you might be either very trained or getting confused all the time anyway, just because it's so confusing. So yeah, sorry for that. But anyway, what this means is, first of all, we were able to read out the memory. And second, we could now save this. And how do we save this? So there are a few ways of doing that. And one of them is using the tftp put command. So with that command, I can use a running tftp server and send a file to it. Or, well, in this case, send a chunk of data to it and say, okay, now give it this file name. Now the other end will take all of those bytes it's receiving and write that to a file with that given name. However, that is something requiring a bit more setup again. So I haven't connected any network so far. And I would need to set up an FTP server and so on. That's a bit annoying, but I will do so over the weekend. So starting on Friday, we will have a 3-day hackathon with the open source firmware people. And yeah, doing this year will be part of the exercises there. And then I will see what else I can do and maybe prepare something a bit more for the next stream. Anyway, this was already quite a deep dive again. I'm sorry if it wasn't very well structured. This is mostly what is happening here now because I'm not preparing too much, and to be honest, I also find it quite entertaining if you can see, what else I'm trying here. Sometimes you need to be a bit flexible and figure things out, right? So if I already prepare everything, then also maybe I'm spoiling myself. And in that sense, maybe you can also follow some ideas or, figure something out yourself. Okay, so what I'm now also doing is I'm powering off the board because it's actually getting quite warm. They also shipped a fan with the board, if you remember from last stream. It's not really overheating, but yeah, it's probably better to run it with the fan only. So I will keep that in mind also for the future. Now the last thing I want to do for today is actually have a look at the many repositories that they offer from VisionFive. And well, no, that is the board name from StarFive. And let's see if we have something that we can then also look further at next time. So let's close a few things here. Is there a link to GitHub here? Yes. Excellent. So let's look at the repositories. So there is one called OpenSBI, which is what you might recall already. There is something called bootloader recovery, second boot, and DDR init. So those would make very, very interesting starting points for next time. So let's quickly clone those repositories here to my VisionFive directory. Let's say git clone second boot. Done. And again for the other one, I git clone the DDR init. And those went very, very quick, which means they are also very small. And as I said, this is what you want to have in firmware anyway, and typically the case. So you don't have that much space, even though 16 megabytes can be quite much. But yeah, if you want to have something richer in there, you would typically use something like, for example, the Linux kernel, or a full embedded system that is already, offering applications and so on. So yeah, there are quite some things to look at here. One of them is a README. I will quickly use the Glow tool to look at that. Glow is a renderer for Markdown for the terminal, which is very nice. So yeah, things are getting a bit colorful. Like here, for example, it says instructions for cross-compile. So yeah, because this year my laptop is on a different architecture. This is an x86. I would need to compile to a different architecture. And commonly, that is part of what is being called cross-compiling. That can also take a few other meanings, but let's just take that one. Enter the build directory, generate the bootloader bin out file after make. Okay, so let's see if that actually works. So I already have my compiler set up here. Let's see. If I go to the build directory and now I run make, let's see what happens. Oh, it had an error. Cannot read spec file nano.specs. No such file or directory. Okay, that is a bit of a shame. Did we miss something? Could be. Do we have something hidden here? No, doesn't look like it. So sometimes Git repositories are split up into modules, but I don't see anything here. Otherwise you would have a .git modules file, which we don't. Okay, they're describing the update process. So apparently it's related to, it says update UBoot. If you select that, apparently you get into another menu which says update second boot, DDR init boot, or UBoot. This is quite complicated, to be honest. So yeah, let's see, maybe we can actually use a programmer directly, an external one. Okay, yeah, we also see though this here, which we looked at today and in the session from the serial part. It's very interesting. Yeah. So yeah, this is something we may need to figure out. Otherwise, let's keep it at that point here. Now let's have a brief look at the DDR init. They also have a README file. And again, this looks very similar actually to the other directory. It also says enter the build directory, generate blah de blah after make. So let's try doing the same thing. We go to build, we say make. And it says cannot read spec file nano.specs, no such file, a directory. Huh, what a shame. So yeah, I'm not sure what that is. We will figure it out. It could be that the toolchain that is offered by SiFive is a bit different and has this sort of file somewhere, but I don't know. Anyway, what you can see here is the compiler being invoked. So it says RISC-V 64, that is our target architecture. Unknown, that is okay. So we don't know any specific operating system or something to target here. There is ELF, the binary format that I briefly mentioned, and then GCC, that is just the generic name of the compiler. That is for the GNU C compiler. GNU is like a very large project of many, things which can make up an operating system. They even tried to make a kernel at some point, but yeah, it's commonly just used as all the other tools besides the Linux kernel. Anyway, yeah. Let's pick that up again next time. And I would say that's it for today. I was hoping that we could get a slight little bit further and maybe a bit quicker. So yeah, I think I was a bit slow, but we will gain some speed again. So you have the rough information now, how you would dump the mask ROM, and I will do so and prepare that for next time. And then we can have a very brief look at that if we can figure something out. And besides that, yeah, I will see if I can also figure out this nano.specs thing. And then next time, let's see if we can eventually get to the point where we can execute some of our own code. So thank you very much and see you next time.